Well, now, ladies and gentlemen, for the last lecture of this beautiful Tuesday on the subject of boundary regularity for area minimizing currents and a question of Almgren from Zurich, Camillo De Lellis.
Okay, so thank you very much. It's a pleasure to be here. It's actually my first time in São Paulo. It's a beautiful and huge city. So let me start by recalling you something which actually was already mentioned in another lecture, and actually something that you probably all know, but nonetheless. So the original Plateau problem, which is credited to the Belgian physicist Plateau, although it was already formulated before by Lagrange, is the following. So if you're given a curve gamma in R3, you look for a surface which spans gamma and minimizes the area. Okay? So this talk is actually going to be about a more general version of this problem. So a general Plateau problem, as you can easily imagine, is that given an m-1 dimensional surface gamma in an ambient Riemannian manifold sigma, you actually look for the surface T, which is m-dimensional, which spans gamma in sigma and minimizes the m-dimensional volume among all surfaces in sigma which span gamma. I will actually not treat this problem, but I will focus on a variation of it, so which I will call the general oriented Plateau problem. So I'm insisting actually that the given boundary, the given surface gamma is an oriented boundary. It's inside some m plus n dimensional Riemannian manifold sigma, and I'm looking then for an oriented surface T in sigma which spans gamma. So here is actually, this one is a typo, so the boundary of T should be equal to gamma. It's inside sigma and minimizes the volume. Actually, I will call the volume the mass, and I will call the volume the mass for a reason which is which will be clarified in a couple of slides. Okay? So it's obvious that in this situation I've already fixed a notion of what it means to span a certain boundary gamma. So my notion is the usual notion that you encounter in differential topology. So T is a submanifold of sigma, and the boundary of T is equal to gamma in the usual differential topological sense. Okay, so why I'm actually insisting that I want to minimize the mass rather the m-dimensional volume. So let me give you the following example. So here you see on the left and on the right two disks, so two circles actually in the three-dimensional space. So there are two circles which are lying on two parallel planes, and the center of the centers of the two circles are actually lying on the same line, which is perpendicular to the two planes. Okay. So on the left, you see a situation in which the orientation of the two circles is one opposite to each other. So this circle is oriented in this way, and this circle is oriented in this way. Okay, as it is very well known to, especially to a lot of experts in the audience, if the two circles are sufficiently close, it is convenient, so the minimizer of the area among all surfaces which bound these two circles is okay, so it's actually this one on the back. So it's actually a surface like this, which is in fact a piece of a catenoid. Now, of course, if you actually pull the circles very far apart, then it's more convenient to take a disk over here and a disk over there, and this would be actually a better competitor compared to having a lateral surface here. Okay. But if the two circles are oriented in the same way as it is actually in the right picture, then there is no lateral surface which is picking the two boundaries, and you're actually forced, even if the two circles are very close, you're actually forced to take the two disks as a minimizer. Okay? Good. Now imagine that you're taking the top disk or the top circle, and you're actually sliding down until the two circles become coplanar. Okay? And of course you do the same operation on the left. So if you do it on the left, when you move the circle, the top circle towards the down circle, when they become coplanar, the minimizer is converging to a corona, whereas if you actually do it on the right, the minimizer is converging to a smaller disk over here, which is superimposed to a larger disk. Okay? So therefore, if you want some kind of stability for the solution of the Plateau problem, what you discover is that you have to count the inner disk twice, right? Once because of the lower disk, and the second time because there is the top one, which is simply sliding down. Okay? So from this example, you actually learn two very simple things. So the first one is that if you're trying to solve the oriented Plateau problem, it actually makes a lot of sense to introduce integer multiplicities. So surfaces actually might be counted with more than one. Okay, so that's why I was actually calling the m-dimensional volume mass, because I'm thinking that the surfaces actually come with a certain multiplicity, and you're multiplying the m-dimensional volume times the multiplicity that you're given. So that is really the quantity that you want to minimize. Okay, and then the second conclusion is that actually solutions of the oriented Plateau problem might have two-sided boundaries. So if you look on the right, on your right, to a point which is in this portion of the boundary, then you will have that here your surface is a classical manifold with boundary, so you have nothing on this side, and then you have the surface with multiplicity 1 on this side. But if you look at points P which are lying on this inner circle, you will actually see that you have, if you kind of zoom into a point P over here, in the limit, you will see a plane, a half plane, counted with multiplicity 1, somehow on this side, and another half plane counted with multiplicity 2 on this side. Okay? So in the future, we are going to call situations like this two-sided boundaries, right? So here I have a point P where, although this point is a boundary point, the surface is lying actually on both sides of the point, right? So contrary to this situation over here, where the surface is lying only on one side. Okay, so points like in here will be called one-sided boundary points. Okay, so now the first question that you might ask, of course, is the question of existence. So if you're trying to minimize the m-dimensional volume or the mass in this context, is there actually a minimizer? And this was tackled in the 50s and 60s by works of De Giorgi and Federer and Fleming. So De Giorgi's work actually was concerned with the case of hypersurfaces. So the minimizer that you're looking for has actually codimension 1 in your manifold. And the general theory was developed by Federer and Fleming in 1960. Okay, so what you're looking for is, in some sense, the definition of the most general-oriented surfaces which have finite volume and whose boundary has finite area. Okay, by also taking into account that you're allowed to pick up higher, multiplicity higher than 1 for pieces of the surface. Okay, so these objects, the most general objects that you can introduce in this sense, are called, in geometric measure theory, integral currents. I'm not going to give you actually the exact definition of integral currents, but so there's a fundamental theorem which comes out of compactness. So the space of integral currents is suitably compact, and suitably compact means if you control the mass of the boundary and the mass of the surface for a sequence of surfaces, then up to subsequence, and if you're staying, for instance, in a compact subset of Riemannian manifold, you're converging in a suitable sense to an integral current, which is this kind of generalized surface. Okay? Since actually it's pretty easy to see that the mass is lower semi-continuous, once you have this compactness theorem, you have the existence of minimizers. And now, although I'm not going to give you the definition of integral currents, you can think about them as a kind of closure of the space of smooth oriented surfaces with multiplicity under a suitable notion of convergence. So in particular, you have something which is called the deformation lemma, which tells you that if you have a general integral current, you can actually approximate with kind of more regular objects. Okay, so you can think about the space of integral currents, therefore, as the variational relaxation of the Plateau problem for oriented surfaces. Good. So the theory of integral currents is homological. So you can actually build the classical homology of Riemannian manifolds by using the space of integral currents. This is one of the famous results of Federer and Fleming. And for this reason, it has actually several striking applications to geometry and mathematical physics. So they come up very natural when you want to select, for instance, a representative in homology class, or when you want to sort of argue by having a preferred surface which is taking a certain boundary. Okay, so there are really many striking applications. Okay, so the second question that you certainly want to tackle once you have an object which is a minimizer is whether you have more regularity than the space of general currents that you started with. Okay, so remember that you have a relaxation of the original problem. So if you think in terms of an analogy, kind of the nicest analogy that can come to your mind is the problem of minimizing the Dirichlet energy. So in order to minimize the Dirichlet energy, you might introduce the Sobolev space W12 or H1, which is the space of functions over which the integral of gradient of u squared is finite. But of course, if you take a minimizer, the minimizer is a harmonic function, is way more regular. In fact, it's real analytic. Okay? Of course, the question of regularity is not only interesting as a theoretical question for analysts, but also if you are a geometer and you want to sort of infer further geometric conclusions for the minimizers, then having regularity allows you to perform all sorts of computations. Okay. Unfortunately, the solutions of the oriented Plateau problem admit interior singularities. So in the codimension one case, the first singularity that you encounter is for 7-dimensional surfaces in 8-dimensional spaces. So this is a very famous example, is the cone over S3 times S3 in R8. It's called the Simon's cone, and it was proved in a famous paper by Bombieri, De Giorgi, and Giusti that actually this object is a solution of the oriented Plateau's problem in the 8-dimensional space. And it has a point singularity at the origin. Okay? It's even more true in higher codimension. So there's a classical theorem of Federer which actually says that every holomorphic submanifold of a Keller manifold is, given its natural orientation, an area minimizing surface. So a solution of the oriented Plateau problem as well. So now this means that if I take any holomorphic curve in C2, I have a 2-dimensional area minimizing surface in R4. And of course, these objects might be, from the point of differential topology, singular, meaning you can have points where, for instance, there are crossings of planes, but you might have actually also points where you have branching singularities. Okay? So a typical example is this one. So you have the curve, the holomorphic curve, which is actually an algebraic curve, where you take ZW in C2 and you impose that Z square is equal W to the power 3. In the neighborhood of the origin, there is no way of writing, in any neighborhood of the origin, there is no way of writing this surface as the graph of a single valued function, no matter how you choose the coordinates. Okay, so for reasons which will become clear in a couple of slides, let me also stress that you have examples like this, right? So this is a more complicated algebraic curve. It's obviously singular because 2018 is not divisible by 3, if I didn't make a mistake. No, it's correct. And so now, once you actually know that there are singularities, you could ask the next question, which is how large is actually a singularity in general, right? So, okay, so there are singularities, but if the singularities are small, and if you can analyze the structure of the singularities, of course, you can still infer a lot of conclusions. Okay, so in fact, the current state of the art for interior singularities tells you that the 2 examples that I gave you are also optimal. So you cannot actually make the singularities dimensionally larger than the 2 examples that I showed you. In particular, if you are dealing with minimizing hypersurfaces, then the codimension is really, then the dimension of the singular set is really tiny. Okay? So if you are in codimension 1, so if you're looking at area minimizing oriented hypersurfaces, the singular set of an m-dimensional minimizer has dimension at most m-7. So the point singularity in the Simon's cone, which is a 0-dimensional singularity in a 7-dimensional surface, provides you an example that this result is sharp. And this is actually the combined effort of several outstanding mathematicians in the 60s and 70s. In higher codimension, you know from the start that the singular set cannot be as small as for hypersurfaces because you have these holomorphic curves in which you know that the singularities have real codimension too. And this is also optimal. So there is a famous theorem by Almgren, proved around the 70s, and I think typewritten in 1980, which tells you that the singular set of an m-dimensional minimizer has dimension at most m-2 in general. And there is a refinement of this theorem, which is due to Chang in 1988, which tells you that if you are in the two-dimensional setting, the interior singularities are actually discrete, so they are isolated. Now note, they are not finitely many, because actually the theorem of Chang does not exclude that the singularities might kind of accumulate towards the boundary. But as long as you stay in the interior, singularities are isolated. Okay. So now, there are some issues actually, although the theory seems complete. Well, first of all, there is a big dichotomy between the codimension 1 situation and the higher codimension. So the codimension 1 is really well understood. I mean, if you look in the literature, there are many streamline proofs in several textbooks. The proof of regularity has been generalized to several other situations. For instance, you can tackle stable surfaces by a famous work by Shen and Simon. And this has also very powerful applications. And last but not least, the methods with which you actually could achieve this theorem, this fundamental regularity theorem, has had a great influence in the mathematical literature, both in differential geometry and in partial differential equations. In fact, a lot of things that we now give for granted when we're dealing with problems in geometric analysis and we analyze singularities, they come historically from the context of area minimizing surfaces, like epsilon regularity theorems, somehow stratification theorems, analysis of tangent cones, certain rescaling arguments, and so on. Now, the higher codimension is comparably poorly understood, at least till now. So first of all, the original work of Almgren was huge. So it was 1,728 typewritten pages. And the proof, of course, is extremely complicated. Up to a few years ago, there were no generalizations. I mean, there was this proof for this particular, for this very fundamental case, but as soon as you moved a little bit far away from the area minimizing situation, you didn't know anything. And people were somewhat scared to apply. So although there are very nice geometric applications that came. For instance, there are work of Taub's, especially the work of Taub's on the equivalence between Gromov and Seibert-Wichten invariance, and then further work by Rivière and Tian and Rivière. Of course, when you're trying to apply, such a big machinery to prove something, you are slightly nervous, right? Okay, so why is the higher codimension so difficult? So why actually is it so difficult to prove the regularity or to get the optimal regularity theory in higher codimension? So let me just give you the most basic idea why this is difficult. So the problem is that branching singularities might be very high order perturbations of regular situation. So if you look at the Simon's cone, you could just say that the singularity of the Simon's cone happens at order 1, right? So in 0, I don't have a linearization of my surface. I don't have a nice linearization of my surface. So if I had a linearization of my surface, there would be a tangent in 0, which is a plane, which is a 7-dimensional plane. And obviously, since the Simon's cone is a singular cone, it's simply invariant under the scalings. So if you just zoom into the singular point 0, you just find always the same object, right? So it has no tangent plane. So there are no derivatives somehow, no first-order derivatives. But now, if you look at the example of the holomorphic curves, you could have such a beast, for instance. See over here? So this is actually singular, but if you take the square root, the singularity as order k plus 1/2. So there is a whole hierarchy of Taylor expansions that you can, or there is a whole hierarchy of very good approximating smooth surfaces in a neighborhood of the origin before you actually see the singularity. Right? So there will be approximating surfaces of order 2, approximating surfaces of order 3, up to order k. And then the first time that you see the singularity is actually at order k plus 1/2. So when you try to approximate your surface with the graph of a polynomial that has order k plus 1, then you will see that actually there is something happening over there. And this k is arbitrary, right? So the singularity in this case is order higher than k. And there is a whole expansion of regular orders that you have to understand before actually getting to the singularity. Good. So now, there have been new developments, though, in the literature. So for a long time, I was trying, together with my former student, Emanuele Spadaro, to get a shorter proof of Almgren's theorem. And we have succeeded in that, actually. Back in 2015, we have a considerably shorter proof of Almgren's theorem, although it's still based on some of these fundamental ideas. And subsequently, we had further developments. So, for instance, together with Lucas Polaor, we've actually able to generalize Chang's theorem to situations in which the area is not really area minimizing. So, in particular, in these papers, we handle 2D semi-calibrated currents, improving, well, generalizing previous results of Bellettini and Riviere, and three-dimensional cones. So, cross-sections of three-dimensional cones. Now, we know if these cones are area minimizing, they have isolated singularities. Actually, Polaor in 2017 also handled the case of semi-calibrated currents in any dimension. Of course, once you have a theorem which is telling you that the singularity has a certain dimension, you wonder whether you can say more. For instance, whether you can have rectifiability or whether you can have more structures for these singularities. And actually, this is possible, at least in a toy model, which is related to the to Almgren's regularity theory. So here I'm citing two papers by Krummel and Vikramasekera, and one joint work with Marchese, Spadaro, and Valtorta. These two results, actually, they are none is included in the other, and they have non-empty intersection. But I don't want to go into the technicalities. Then there are some generalizations of these concepts to, say, linearizations of the area functional in other around other cones. And then a forthcoming theory which is tackling the regularity for minimizers mod P, in which you actually constrain your set of multiplicities to be taken mod P. And this is actually tackling open questions which are around since a paper by White in 1986. But what I want to talk about today is actually a further work which is based on this regularity theory, which is answering to an open question that Almgren himself has towards the end of the monograph. So when I'm saying towards the end of the monograph, actually, if you take out the appendices, so he states this question in the penultimate page of the monograph. Okay, so here is a question which is very natural. So assume your boundary for the solution of, you're solving the Plateau problem, and your boundary is a connected surface with multiplicity 1. Then, although I've given you examples in which you might have minimizers which have higher multiplicity, so remember these two disks which are on top of each other, you would expect that is only happening if your boundary data is disconnected, right? So if your boundary data is connected, you're expecting that is not going to happen. So you expect that the minimizer is connected and has multiplicity 1. Okay. And intuitively, the answer to this question is yes. And how you would like to argue? Well, say that you had full regularity, right? So if you have a regular piece of the surface, the multiplicity cannot jump along this regular piece, right? So the multiplicity is constant over there. Now, the boundary of each connected component of the regular pieces must be contained inside your given boundary data, okay? And by connectedness, it must take the whole boundary data as a boundary. So what you actually discover is that if you have full regularity, your minimizer should be decomposed into connected components. Each connected component is taking the boundary, and it's taking the correct boundary with a certain multiplicity. And then the sum of the multiplicities, which might be positive or negative, has to give 1. Okay? But if you have such situation, of course, you could just say, wait a second, take one of the connected component. If you're counting it with a certain multiplicity, divide by that multiplicity, and then that connected component is a competitor for your minimizer. It has strictly less area if the multiplicity is higher than 1 and if there are more than one connected component. That cannot happen. Okay? So there is only one piece and it has multiplicity 1. So of course this is possible if you have full regularity. And now you can ask, the first question is, so what is happening, given the current regularity theory that we have, what is happening to these points A, B, and C? So first of all, it's not true in general, if you don't have a powerful enough regularity theory, that regular pieces with different multiplicities should be totally separated. So look at this example. So here I have a segment with multiplicity 1, another segment with multiplicity 2, and then I have a segment here with, a segment with multiplicity 1, a segment with multiplicity 1, and another segment with multiplicity 2. So they are coming together, and then they join, and they go on. So this oriented one-dimensional surface has boundary here, and then 2 times boundary here, but has no boundary in this point over there, right? So because the incoming segments, the boundary from the incoming segments can cancel with the boundary from the outcoming segment. So here the singularities are actually, the multiplicities are actually jumping. But of course what you can immediately observe is that if you have a jump of multiplicities at interior singularities, well, the singularities must be large. So in an m-dimensional oriented surface, the multiplicity can jump only along m-1 dimensional singularities. And now Almgren's interior regularity theory actually tells you the singularity in the interior has dimension m-2. So this cannot happen. The regularity theory that you have in the inside is powerful enough to tell you that the first point of your proof is actually still correct. Okay, what about the second points? Well, B and C, so the conclusions at the boundary are certainly okay if there are no boundary singularities. And there is a classical result by Allard and Simon in 1980 which tells you in codimension 1 there are no boundary singularities. So in codimension 1 the solution of the oriented Plateau problem is always fully regular at the boundary. Okay? Now for me regularity it means that there is a neighborhood of your point in which what you're going to see is a manifold, either the manifold has multiplicity 1 and is taking the boundary, or it has a situation like the two-sided boundary points that you have seen. So there is a single minima surface and it is counted with multiplicity k on one side and k minus 1 on the other side of the boundary. And the boundary is inside this surface. So this is a regular point for me. Okay, unfortunately, the Allard-Simon theorem is actually false in higher codimension. So you have the existence of even real analytic curves in the Euclidean 4-dimensional space which allow for 2-dimensional minimizers with boundary singularities. Okay, so one idea is to take a regular closed curve gamma which is contained in your algebraic surface, which has a branching singularity at 0, and which is passing through 0. So now I'm actually very bad at drawing, but the idea would be something like this. So, okay, so here you have, say, your disk. Here you have a branching, right? So you start at some point here. You go around the branching for a certain amount of time, and then you join it through the singularity. Okay? So this means that this curve that I've drawn actually is going one time around one branch, and then somehow there's a, if you're going to project this curve down, it's covering 2 times this part of the circle, and it's covering only 1 time this part of the circle. And then there is the projection of the boundary, which is given by this line connecting them. Okay, so this surface, so this curve, which is going to be CK, where K is this parameter, passes through the origin, and the minimizer is going to be the portion of your branching surface which is bounded by this curve, which is topologically a disk. So this is a minimizer which is a disk and has a branching singularity at the boundary. Okay? Now, it can actually, so this example can actually be made C infinity. So there is a paper by Gulliver which does that. But it cannot be made real analytic. So if you are real analytic curve and the topology of the minimizer is finite, there is a beautiful paper by White in 1997 which tells you that there are no boundary branch points. But if the curve is real analytic, there might be actually points at the boundary where you have self-intersections. So you might have a point of the boundary which is intersected by a part of the surface which is coming from the interior. So that might happen, and that is also singularity. Okay, so this is the bad news, but on the other hand, the theory of currents is so powerful that one lemma by Federer actually tells you, in the sketch of proof that I've given you, you actually don't need full regularity at the boundary. It suffices to have one regular point at the boundary to actually make all the theory go through. So if you combine the interior regularity by Almgren with the existence of a single boundary regular point, then you can actually claim, or you can actually infer that your minimizer has density 1 in the interior and consists of a single connected component. Okay? So you just need one boundary regular point. Now, the problem is that up to now, the state of the art of the theory is that in higher codimension, so with in codimension 1, Hart-Simon is giving you full regularity at the whole boundary. In higher codimension, you don't know the existence of a single boundary regular point. So the minimizer might be actually irregular everywhere. Okay? Okay, so now it's just a little disclaimer. So I was giving actually the same talk somewhere else, and in the end we will see that we can actually answer positively to the question of Almgren in general. And the reason why we can answer positively to the question of Almgren is because I'm going to give you a regularity theory which produces regular points somewhere, right? And then at the end, somehow, some people told me, okay, but look, this is a huge proof for a, seemingly elementary question, which possibly has maybe a 2 pages proof instead of a 200 pages proof as we have now. That is correct. So the point of my talk is not that I actually developed the regularity theory at the boundary to solve that particular question. We actually were developing this regularity theory for like 4 years, and then I bumped into the question by reading the book a little bit more carefully. And then I noticed, we can actually solve that question. Okay? So this is just to illustrate the fact that even if you want to conclude something innocent, you do need some boundary regularity, right? So, and maybe also to keep you awake with an explicit example of a geometric goal that I have in mind, rather than proving some ugly analysis estimates somewhere. Okay, good. So, recall now the example of the one-sided and two-sided again, right? So, if you remember in our example, so this is a two-sided, here you have two-sided boundary points, and here you have only one-sided boundary points. Okay, so now if you take a point P, which is in your boundary gamma, if it belongs to the inner circle of the right example, so what we say in geometric measure theory is that the tangent cone to T at the point P is contained in a single plane pi, so it's a flat tangent cone. But instead of being a half plane, it's a half of pi is counted with multiplicity twice, and the other half is counted with multiplicity 1. So we will call such points two-sided boundary points, but we will also call them flat, meaning that the tangent cone is flat, right? Because you could have actually points where the tangent cone is not flat and the surface is lying on both sides. Okay? Now, there is a fundamental problem here, that is at points which are, at points at the boundary which are flat and two-sided, I cannot claim that I have full regularity. So this example that I gave you of the curve which is going in a weird way around your branching, right, and then it's cutting through the singularity, I get actually a boundary point where when I zoom into it, I see a tangent cone which is 2 times half a plane and 1 time the other half of a plane. So when I actually zoom in and look at the tangent cone, I see the same tangent cone as for the regular boundary points. So the tangent cone alone is not actually able to distinguish between regularity and singularity. Okay? It's the same thing that happens in the interior, where I just told you that branching singularities are very high order perturbation of regular things. So in the interior, if I have a branching point, I can have a tangent plane, I can have a tangent parabola, a tangent order 3 polynomial, but nonetheless be actually singular. So the same happens here. So the singularity at 0, which is created by this curve gamma, which I gave you in the example, has a tangent cone which is actually flat. It's flat but two-sided. So now, a fundamental theorem of Allard, which is called in the literature Allard's boundary regularity theorem, actually tells you that if you have a tangent cone at the boundary point and the tangent cone is a half plane, so if the tangent cone is flat and one-sided, then the point P is actually regular. Okay? And actually Allard proved for area minimizing current, actually he proved this theorem twice. So first of all in his PhD thesis, and then later in 1974 he generalized this statement to stationary integral manifolds which contain actually area minimizing currents as a particular case. So in his 1974 paper, he doesn't need the object to be a minimizer, he just needs the object to be a critical point. Okay, now, from now on, points P, as in Allard's boundary regularity theorem, will be called point of density 1/2, right? For a very good reason. So if I look at the total volume which is contained in a very small ball, right? So the total volume of the surface which is contained in a very small ball is essentially half of the volume of the disk, right? So at point P in the interior, where you have multiplicity 1 and where you have regularity, the volume at small scales of the surface will be the volume of a single disk. And those are multiplicity 1 points. So at the boundary, these points will be called multiplicity 1/2. And there's a beautiful generalization of a theorem by Almgren. So this generalization is given by White. And it says, I mean, as a corollary of this stratification theorem, it says, if you can exclude two-sided flat boundary points, the set of boundary singular points has dimension at most n-2. So if you could actually exclude these ugly branching at the boundary, you would be able to give the same dimension estimate for boundary singular points as you have in the interior. Okay? Now, in some cases, and this is still a consequence of work of Allard, actually you can have full regularity. So, for instance, one interesting case is when your boundary curve gamma or your boundary object gamma lies on the topological boundary of a uniformly convex hypersurface. Okay, so now in there you actually have full regularity. So here is a lemma by Allard which tells you that if you have an open set which is bounded and uniformly convex, and if the boundary data gamma that you're interested in is contained in the topological boundary of this open set, then any area minimizing current which bounds this, so here is again a typo, it bounds gamma, not sigma, has density 1/2 at every point. And then with the theorem, you actually conclude that every point is regular. So if you're lying on the boundary of a convex set, you have full regularity. So what is the reason for this? The idea is that the convexity of the set, right, gives you, through a very simple argument, a barrier for your minimizer. So your minimizer has to lie inside the convex set. And once the minimizer has to lie inside the convex set, this means that the point P cannot be two-sided. Okay, so there is a little bit of extra work to actually rule out non-flat tangent cones, but once you have ruled out non-flat tangent cones, once you know that that point P, the tangent cone, is flat, it has to be a half plane, which is kind of coming from rescaling your boundary of the convex set, which is giving you then finally a hyperplane, which is forcing the tangent cone on this side. Okay? Now, this is actually a local condition, and you can generalize it. So with a paper by Hart in 1977, you could use this argument to prove regularity at the outermost point if you are in the Euclidean space. What do I mean by outermost points? So there are points where you can actually have a sphere which is acting as a boundary, right? So for instance, in this example, these points over here would be outermost points, but these points over here would not be outermost points. So Allard's regularity theory guarantees regularity here, and here, and here, but you don't know anything about this side of the curve. Okay? Well, actually, in this case, it's a curve in the three-dimensional space, so you can apply Hart-Simon. So you have to imagine this is in 4 dimensions. Okay? So now, what happens in the standard Euclidean space? You can always have an outermost point, right? So you take the smallest sphere that contains actually your boundary. It touches at one point, and that point must be regular by Hard and Allard. But if you are in a general Riemannian manifold, of course, you cannot use this argument, right? So if you are, I don't know, in a Riemannian manifold which is complete and it has a foliation with convex surfaces, then you could do it. But for instance, if your manifold is closed, then you don't have anything like that. And so this is the situation I was telling before. If you have a closed manifold and you have a minimizer which takes a certain boundary data, maybe if your manifold is 4-dimensional and the boundary data is a curve which is not contained in a very small ball, maybe there is no regular point at the boundary. So this is the situation for the regularity theorem up to now. Okay, so now I've actually made what my first postdoc advisor calls a capital sin, because this is the main theorem of the talk, and it's coming at minute 40. So according to Stefan Müller, I actually should give my main theorem within 10 minutes from starting of the talk. Anyway, so what we actually can prove in a joint work with Guido De Filippis, Jonas Hirsch, and Annalisa Massacesi, which is not yet available on the web. Hopefully, in the next 2 weeks, we are done. We are just proofreading the last the last two sections. So the theorem actually tells you in any Riemannian ambient manifold, in any dimension and codimension, and for any smooth boundary, any oriented solution of the Plateau problem is regular at the dense, relatively open set of boundary points. Okay? So, in particular, there is at least one point where you're regular. But in fact, it tells you much more. So boundary irregular points can only be rather scattered. At least topologically, they must be a meager set, so rather small. Note that this is actually giving you interesting new information, even in the case where you have outermost points. So if you go back to this example, Allard was giving you full regularity over here, but it was giving you no information here, where you have no barriers. So now our theorem tells you here there might be singularities, but there is a dense open subset of this curve where you actually have regularity. Okay, so here I'm saying smooth Riemannian manifold, smooth boundary, there is a certain precise regularity that you can ask. It's actually 3 derivatives and some further continuity of the third derivatives, both for the Riemannian manifold and for the boundary. Now, important actually, so I'm crediting the 4 of us, but this theorem is possible because of the PhD thesis of Jonas Hirsch, where he actually solved some boundary regularity problems for harmonic multivalued functions, and these were the starting point of our work. Okay, so now, let me actually tell you that this is way trickier than interior regularity. In fact, I'm quoting this paper by White in 1997. This is the paper where he actually showed that if you have a real analytic curve and an area minimizer with control topology, then there is no branching point at the boundary. Okay? And notice that we cannot apply actually this theorem in our context, because we don't know that, we know that our solution is regular in the interior. Even if you are in 2D, it has kind of isolated singularity. But we don't know whether there is a sequence of necks which is accumulated to the boundary. So the topology of our solution might be actually infinity. It does not have a fixed genus, unfortunately. And this is a big open problem. So, but in fact, so here I'm quoting White, which has a very good reason. He gives examples for saying that proving partial regularity for integral currents at C infinity boundaries seems to be much harder. But in fact, we can give an even more specific reason why this is harder. So we have an interesting example in the 2-dimensional case. So as I told you, Chang's theorem is telling you interior singularities for 2-dimensional minimizers are isolated. Now we have an example which says that this is false at the boundary. So there is a C infinity embedded curve gamma in R4, and an area minimizing 2-dimensional current T in R4, such that T has a boundary singular point which is not isolated. So, in particular, we can actually make this example so that the boundary singular point is approached at the same time by a sequence of interior singularities and by a sequence of boundary singularities. So this means even the interior singularities, you cannot claim they are finitely many. So they can be countably many, they can be infinite, and they must then accumulate, of course, to the boundary according to what you know from Chang's theory. Now, notice that I'm saying C infinity here. So this is, I mean, it's very likely, it seems really, really likely that this is false for real analytic. In particular because the point at which we have the accumulation of singularity is a branching point. So a posteriori, I mean, this actually, the example that we have as a minimizer is a disk. So certainly, White's theorem is telling you we cannot engineer this example and improving from C infinity to real analytic. So in the real analytic case, one would really expect that if you have a real analytic curve in R4, of course here we're talking about embedded curves, then the singularities are finitely many, and there are finitely many interior branch points and only crossings actually at the boundary, and finitely many of them. But we're very far actually from even being able to attack this problem for the moment. Okay, so now the boundary singular points of the example actually have density 3/2. And the example would then be the analog of interior singularities of density 2, which accumulate to a point of density 2. Okay, so this is rather a little bit technical, but my fault. Okay, maybe my fault, sorry. So now, if you know Almgren's theory, actually there is a first step in his interior regularity theory which rules out this behavior of accumulating singularities for what are called two-valued harmonic functions. This is actually the deus ex machina of the regularity theory. I mean, this baby case is what triggers the big, Almgren's big regularity paper. So our example is actually also a graph of a two-valued harmonic functions. And so what you actually know is that the conclusion that there are no singularities accumulating, which was true in the interior for two-valued harmonic functions already in Almgren's theory, is false at the boundary. And once you actually look at this, you would pessimistically think that it's therefore just impossible, plainly impossible to modify the Almgren's regularity theory in order that you can actually attack the boundary regularity theory. So, nonetheless, it's actually possible to do something like we have done, but you need rather heavy adjustments, and in fact, you need rather new ideas to do it. Okay, so now just the last 5 slides, only for experts who have been probably sleeping up to now, in which I have to show some PDEs because then otherwise my colleagues will think that I'm doing very soft analysis. I cannot actually stand that, right? So now, okay, it says for experts, but it's not that bad actually. Okay, so here is a cute toy problem. So if you want, I mean, if you were okay, let's try again. Maybe the last 5 minutes is still okay. Okay, so, I mean, if you look at our examples, our singularities were always branching of holomorphic, curves, right? So first thing that you know, of course, is the following. So if you have an holomorphic submanifold, there is no way a sequence of branchings can accumulate in the interior to a branching point. And what is the reason for this? Well, because this would be like having a sequence of zeros of an holomorphic function accumulating to 1, 0, and that is impossible. Well, that is impossible. Yeah, but I'm afraid it's going to be just 1 minute and then it goes again. Okay, so now, of course, holomorphic functions, are nice, but they're more like first order elliptic PDEs. The problem of minimizing the area or having a stationary point for the area is more like a second order elliptic PDE. So an analog would be the following toy problem on harmonic functions. So assume you have an harmonic function u on some domain omega. And assume you have an interior point, say the origin in omega, such that u of 0 is equal to 0. Okay, now, in the case of holomorphic functions, if a 0 is an accumulation of other zeros, what you know for the holomorphic function, or what you know for a smooth function at that point, is that the function has an infinite order of vanishing at that particular point. So you can ask this question, which is a classical unique continuation question. If you know that at the point 0, u of x is equal to, it's vanishing faster than any polynomial, so 0 is a 0 of infinite order for u, then you should be able to prove that u vanishes identically. And of course, there's a kind of trivial solution to that. The harmonic function is make the Taylor expansion at that point, and the Taylor expansion is giving you one first non-trivial polynomial, and you cannot go to 0 faster than that first non-trivial polynomial. Okay? So now, a wonderful discovery of Almgren is that there's actually a very simple way of proving this without claiming any real analyticity for harmonic functions. And this is where his frequency function actually enters. So you consider this quantity, which is called the frequency function, is the ratio of the Dirichlet energy in the ball of radius r centered at 0 with what is called the height function, so the integral over the sphere of modulus of u squared. And here you have just a normalized power of r. So now this function is monotone non-increasing, and this is just a calculus computation. I could say a calculus exercise. I've actually given to calculus students, but nobody solved it. Nonetheless, it's a tough calculus exercise. Okay, and the other thing which is interesting is that now that you know that this guy is monotone, you can actually compute its limit. Its limit for an harmonic function is the order of the first non-trivial harmonic polynomial in the Taylor expansion at 0. So now, since your function is monotone, this k is finite. So you've captured actually the order of vanishing of your function without making a Taylor expansion at the point, without using real analyticity. Okay, so now, what is the toy problem for the boundary regularity theorem? So, assume actually that your point 0 is at the boundary of omega, and assume that u vanishes at the boundary of omega. Now, omega, of course, does not have to be a bounded set, otherwise the harmonic function is anything equal to 0. Okay? So think about an infinite set, and it has a certain boundary, and the function actually vanishes at the boundary. So can you prove the same theorem? Can you prove the same unique continuation theorem? And now the monotonicity of the frequency function actually does not help you, because if you look at the proof, it fails at the boundary. So it does not always fail at the boundary. If the boundary is straight, of course, it actually works. If the boundary is straight, you can actually use Schwarz reflection, right? And it's like having the point 0 at the interior. But if you look at the proof, that is pretty much the only situation in which actually the proof works. Okay, so here is actually a solution which it took us some time, but that we can give in our paper to this problem. So, which of course you can solve in several other ways, Kahneman estimates, whatever. So this is just as an illustration of what we are doing from the PDE point of view. So here we have a kind of two-parameter perturbations of the frequency function. So you see the Dirichlet energy, but there is a weight over here, and there is a weight over here as well. So now what are these d and phi? So phi is a cutoff function. So it's a compactly supported function, and it's depending only on one variable, and we want phi to be non-increasing. So the derivative of phi is less or equal than 0. In particular, this quantity is actually positive, right? Because I have minus phi prime. Now, what is d? d is like a distance function from the origin. So first of all, I want the gradient of d to be tangent to the boundary of omega. And then I want d to behave like modulus of x, asymptotically around 0. So now, behaving asymptotically around 0 as modulus of x, it means it's modulus of x plus a higher order perturbation, which is going as a power which is slightly faster than 1 to 0. And you actually need this not only for the function d, but also for the first and second derivative. Okay, now if you have this object with these conditions, then the conclusion is that this quantity is monotone. And notice that the Almgren's frequency function corresponds to a very particular choice. It corresponds to a choice of phi, which is the indicator function of the ball of radius 1. And it corresponds to a choice of d, which is actually the modulus of x. And I always also want to point out that this idea of putting a smoothed frequency function by using this phi is already present actually in my paper with Emanuele, and it's particularly useful to pass estimates from harmonic multivalued functions to currents. Now here the important point is that the gradient of d has to be tangent to the boundary of omega, and then you have that this quantity is monotone. Now of course you see that if I had a flat boundary, the derivative of modulus of x is actually going radially. So if I had a flat boundary in which I could actually use the Schwarz diffraction principle, then you could use also modulus of x according to this theorem, because the gradient of modulus of x is tangent to the flat boundary. Okay. Now, it's actually interesting, if you take the very same idea, you can use it to give a very quick proof of Allard's boundary monotonicity formulas for the area, for stationary variables. But, the original proof is rather complicated. So, in particular, if you, instead of looking at the exact ratio between the volume of the surface and r to the power, you introduce a suitable weight, you can actually get an elementary proof of monotonicity by using first variation arguments, as it happens in the interior. Okay, so I guess this is all I wanted to say. I wanted to finish slightly earlier than this, but I'm still on time though. Thank you very much.